Hi, I'm Mark Feldman, Senior Staff Engineer Manager at Qualcomm Technologies. Today I want to talk to you about the triangle sample in the Arduino SDK for Vulkan. The triangle sample in our Arduino SDK for Vulkan is our version of showing a very simple Vulkan rendering example. We've tried to use the smallest number of Vulkan setup operations and keep things simple. The geometry we're drawing consists of 3 vertices with 2 attributes and no index buffer. There's no object abstractions or frameworks in the C++ code. We've even pre-processed the vertex and fragment shaders to SPIR-V bytecode, so there's not a lot of shader code to worry about in this first example. The resulting rendering draws the triangle with interpolated colors. The triangle sample is a good sample to start exploring Vulkan with. Let's make sure you can launch the application and start debugging. Refer to the previous video in this series on using the Arduino SDK for more details. First, we'll launch Android Studio and open the triangle sample. Next, make sure your mobile device is connected and recognized with AVB. Use the app native configuration for debugging and set some breakpoints, and then select Run. You should be able to debug the code, examining values, and step through this sample to study how it works. I wanted to point out how the C++ Vulkan rendering code is integrated into an Android application. The sample makes use of Android Native Development Kit, NDK. Most games which require the use of native code, such as C and C++ rather than Java, which use advanced APIs like Vulkan, and are CPU intensive, are prime reasons for using the NDK. We use the NDK in all of our Vulkan samples. The files Android native app glue.c and .h from the base NDK's native activity sample are all unmodified. They are useful boilerplate code and shouldn't be modified. Take a look at the Android main function and think of it as your actual main function. It receives an Android app structure with a few pieces of useful data about the Android window we'll be rendering to. Most importantly, you can see how the triangle sample's initialize, draw frame, and teardown functions are appropriately called depending on the Android command state sent to us. Shader.h contains compiled SPIR-V bytecode. SPIR-V is an intermediate format for storing shader code in Vulkan. We're showing the bytecode string for the vertex shader and the bytecode string for the fragment shader. It was created with a library called GSlang, which we'll cover in a future video. GSlang is used to convert GL/SL shader code into SPIR-V. We don't expect anyone to actually embed code like this into a real application. We just did it in this first sample to help simplify the code and avoid dealing with shader compiling for the time being. This will allow us to focus on pure Vulkan code first. The original vertex and fragment shaders are included as separate files in the project for reference. The VK sample class comprises most of the logic for the sample. Sample.cpp and sample.h are 2 files which implement this class. The key functions are initialize, which initializes Vulkan for rendering, draw frame, which performs the rendering, and teardown, which cleans up the Vulkan objects. Most of the member variables store various Vulkan objects. Additionally, the triangle geometry is defined and the Android native window is stored, and there's also a few timing-related variables. Quite a lot needs to be initialized to do rendering in Vulkan, so we've broken down the steps into several slides. First, we're creating the Vulkan instance, surface, device, and queue. Next, we'll create a swap chain. Next, command buffers and vertex buffers. Next, descriptor layouts and pipeline layouts. Next, the render paths. Next, the pipeline. Next, frame buffers and synchronization. And lastly, we'll construct a command buffer with all the commands needed to render our triangle. Android main has hooks that take care of most of the messaging handling from the Android app. The key piece Android main passes to our initialization function is a pointer to the Android native window. We create a Vulkan instance, making sure to enable 2 extensions, VK-KHR Surface and VK-KHR Android Surface. We don't enable any layers in the sample. We'll cover both extensions and layers in a future video. Next, we select a physical device. We assume there's just one Vulkan-compatible device available on our hardware. We then create the presentation surface using the Android native window that was passed in. We create the Vulkan device, an abstraction of the physical device on our hardware. We make sure that the VK-KHR swap chain extension name extension is available on the device. We then obtain a queue that we'll use when we submit our Vulkan rendering commands. The swap chain is very important if you want to present images to the screen in an efficient manner. You can think of it as a queue of back buffers, with each frame rendering into a single back buffer at a time, which is then queued for display at the relevant rate. We create the swap chain and retrieve each back buffer image in it. The swap chain is created using a first in, first out present method. The first one sent to the presentation queue will be the first one presented. There are other presentation methods like mailbox and immediate, but on mobile we prefer first in, first out. For the swap chain, we also specify a standard 32-bit RGBA unsigned normalized format. Once we get the swap chain, we create an image view for each image in the chain. Image views provide content into the image. Think of them as a way to represent the contents of an image in a specific and efficient way. We also create a corresponding depth buffer image for each swap chain image. Together, they form a render target that we'll be using. We allocate and bind memory for the depth buffer image. Notice that we could have created a single depth buffer image and shared it among the swap chain images. Also, just to mention that we're using the full screen size as the size of the swap chain buffers, which may not result in optimal performance on devices with large resolutions, but will be fine for this example. We create command buffers that will contain specific rendering instructions. These are created from command pools that we'll also create. We create one command buffer for each swap chain image. We also create a vertex buffer to define the triangle geometry. We then allocate memory for the vertex buffer, map it so that we can access it, and finally copy the predefined vertex geometry and attribute information to that memory location. Once the data is written, we then bind it to the vertex buffer. The attribute information buffer contains the position and color information in a precise format so that the rendering pipeline we'll be creating fully understands how the memory is laid out. If you notice on the first slide, the triangle appears inverted vertically to the coordinates shown here. That's because Vulkan uses an upper left origin rather than a lower left origin, which GL uses. One simple way to account for this in existing GL-SL shaders is to invert the y-coordinate in your vertex shader. Descriptors refer to resources that are used in shaders. Think of them as constant buffers, images, samplers. The descriptor layout is the blueprint of the descriptors describing what types and how many descriptors are defined in a descriptor set. A descriptor set is the actual collection of descriptors that will be accessed by the shader. We generally create descriptor layouts which define which descriptors and how many of them will be needed when a corresponding descriptor set is created. However, in the simple triangle example, we aren't using any descriptors in the simple shaders, so the layouts are empty, even though we're still required to create them. A pipeline layout tells the rendering pipeline what descriptors are in which descriptor sets that will be used when the pipeline is executed. In our case here, we create one pipeline layout that just points to the empty descriptor layout. The render pass defines which types of attachments the frame buffer will be using and how each of the passes will use the attachments. There are two attachments defined in the attachment table: a color buffer, which will be the appropriate swap chain image, and a depth buffer, which will be the swap buffer's corresponding depth buffer image. There is just one subpass in the render pass, which uses both the color buffer and the depth buffer attachments. We create the render pass with a single call to VK create render pass. The pipeline contains all the state needed to do the rendering. There's numerous inputs required to build a pipeline. For this sample, what's important is that we set the triangle vertex input state and the vertex and fragment triangle shaders in the shader stage state. Other inputs to defining a pipeline include assembly state, rasterization state, color blending state, viewport and scissor state, depth stencil state, and multi-sampling state. The pipeline is also provided with the previous created render pass object. The pipeline is created with a single call to VK create graphics pipelines. We create frame buffers for each swap buffer image. These contain the actual attachment views that will be used during the rendering, as well as a reference to the render paths that the frame buffer will be used with. A call to VK create frame buffer creates each frame buffer. We also create two semaphores, back buffer and render, using VK create semaphore. These will be used to help synchronize the rendering. We'll show how those are used in a second. Now we build our command buffers. The overall strategy will be to build one command buffer for each swap buffer image. We'll use Barriers, another Vulkan synchronization tool, to change the image layout. And we'll use a swap buffer's specific frame buffer for each command buffer. We have a set of command buffers, one for each swap image buffer. Each of them gets built in the same manner. We reset and then begin each command buffer. We use two pipeline barriers. The first one changes the image layout of the back buffer from presenting to color attachment. Next, we start the render pass. We specify the appropriate frame buffer for the swap buffer we're building the command buffer for. We bind the pipeline and then the vertex buffers. We draw our triangle, we then end our render pass, and we use the second pipeline barrier to change the image layout of the back buffer from color attachment to presenting. And then we end our command buffer. Finally, we're done with our initialization. After all that setup, the process to render is quite simple. The flow to draw a frame is to acquire the swap chain image index to use next. We submit draw command buffers using the relevant swap chain image, and then we present the back buffer. We make use of two semaphores which are used as parameters in the three functions to help Vulkan synchronize the use and presentation of the swap chain images. The semaphores cause the program to wait until the images are acquired and finish rendering too. Cleaning up a Vulkan application is relatively easy. Virtually every Vulkan object created has the corresponding VK destroy or VK free function. When validation layers are available to use, you'll get warnings if you forget to delete some objects. This is simple to do and good coding practice. There's a lot involved, but hopefully you'll be able to follow now and understand the steps to render in Vulkan. You've seen how to create and synchronize swap chain images. You've seen how to build and submit command buffers for rendering. We'll look at a few other Arduino SDK for Vulkan samples in depth in future videos and cover some more involved rendering scenarios. Thank you for watching. We hope you enjoyed this video. Please visit the Qualcomm Developer Network to learn more about graphics and tools on Qualcomm's mobile hardware.